demonstrations of how I could ask some questions on an exam, a way that I could get a kind of a lot of bang for my buck, if you will. Got a lot of questions that really poke at the concepts without taking a lot of time because I'm already giving you RRA report. Some of these questions you can do out of order. If you started right away before and found these basis vectors, that would answer a lot of the other questions. But they're in this order because you can answer them in this order. Some things are very visual. All right, let's start with the first one. What is the dimension of the column space? What is the dimension of the column space? 2. 2, absolutely. The dimension of the column space is 2. And the dimension of the null space?
2.
Not 2, should be 1 in this case. Dimension of the null space is 1. Now we'll be able to see that more a little bit later as we find these things, but we can actually tell that right away. If we look at our row reduced form, it's telling us which columns from the original matrix, which columns are independent. So this says, oh, the pivot columns are the first 2 columns. That means these 2 columns are linearly independent, and this one must just be some linear combination of these 2. So these are my 2 linearly independent ones right here. So because those 2 are linearly independent, they're going to be a basis for my column space. So I have 2 vectors in the basis, the dimension should be 2. And of course, it also answers this one right away. Find a basis for the column space, it's just these first 2 vectors. Now what about the null space? There's a couple of ways we can get to that. We have a fancy theorem that tells us the dimension of the column space plus the dimension of the null space should be what?
The number of columns in there.
Absolutely, because these are independent variables. This is our free variable. And essentially, the number of free variables we have, that's going to be the number of basis vectors for our null space. So we write out that solution, it will be free variable times some vector, possibly plus another free variable times some vector. Each one of those vectors is the basis vector for our null space. All right, so now we have the dimensions. What about 2? Is this thing invertible?
Yes.
Is this one invertible? Not invertible. So why not? There's quite a few reasons we can talk about for this one too. Certainly doesn't have enough pivot columns. I would need a pivot position in every column, but also need one in every row. And really, I can't even start to talk about it being invertible unless it's n by n. So for all 3 of those reasons right away, we can say no, it's not invertible. Now A is a mapping from where to where. So for this 4 by 3 matrix, this thing maps, takes values from R what to R what?
From R3 to 3.
R3 to R4, absolutely. And if I put a vector here to multiply it by, it would have to be a size 3 to do the multiplication. It would map to a vector of size 4. Find a basis for the column space. Well, we already saw the basis for that. It's just going to be the first 2 columns. So that's my basis for the column space. Now my basis for the null space is a little more work. Now I have to actually find the rest of the solutions here. So I can go to that RREF form, and now I'm trying to find the solutions to AX equals 0. So now it's all reduced for me. I can see this gives me the equations x1 minus 6x3 equals 0, and x2 plus 3x3 equals 0. x3 is my free variable. So my solution to this thing, which will be a value for x1, x2, and x3. Well, x1 is just 6x3. And when I solve that for x1, when I solve for x2, I'll get minus 3x3. And x3 is just x3 is my free variable. So it looks like a basis for my null space will be the vector 6, -3, 1. As I can see that my solution is any multiple of that vector. And then the last question, the column space is a subset of, or subspace of R what, and the null space is a subset of R what. We should be able to look right away at the beginning to answer this question as well. We're saying that it's mapping from R3 to R4, taking x vectors from here, mapping them to b vectors here. Well, the null space is just a set of x vectors, so it must be a subset of R3. And sure enough, we can see that. Right? It's not all of R3, it's just multiples of this vector, but it certainly lives in R3. And what about the column space? Well, that's the collection of all b's. Well, the b's live in R4, so the column space must be a subspace of R4. And of course, we can see that as well when we look at the basis. It's certainly not all of R4. We would need 4 basis vectors to span all of R4. But this is a subspace that lives in R4. So the column space is a subspace of R4, and the null space is a subspace of R3 in this case. And of course, we can now generalize that to be M and N generally. All right, any questions from the warm-up? All right, so that took about 6 minutes-ish for me to go through those. There's a lot of explanation. So this is a problem that I feel I could write on an exam and not take a lot of time to do. Right? Because I already give you the REF4. All the answers are kind of right there if you know what you're looking for. So you should be able to go through a question like that relatively quickly on the exam. Any questions? All right, so our plan for today, I'm going to describe exam 2 a little bit, just real quick. I'm going to take questions from exam 2. If you have any questions about any of the content we've gone through so far, make sure you ask today. Remember, it's your grade that you're going to get in this course. It's your grade on exam 2, so if you have any lingering questions, just ask. With whatever time we have left, we'll maybe launch into chapter 6, 6.1. We're talking about do kind of a general overview about chapter 6, and then we'll talk more specifically about 6.1, where we talk about length and angle for vectors. Okay. So the exam is going to run just like I did last time. It's going to be closed book, closed notes exam. 1 hour to do it, but I'll be in early. So if you want to come in early and get a jump on it, you're more than welcome to. If you want to come in early but have some sort of conflict, just let me know. I'm sure we can work something out. I don't like time to be a factor. I know that the more work you check your work, it will be. So come in early if we can. Can use a calculator, but you need to show your work. You will need to specify when a calculation is done via calculator. Right? So in other words, you're going to see on the exam, I'll say show all work, probably everywhere. But I don't expect you to necessarily do the row reduction anymore. We did that in the last exam. If I want to see row reduction, I will tell you show your row reduction here. Okay, so I will specifically tell you to do that as far as work goes. But otherwise, say you're going through and finding an eigenvalue, you get a polynomial, you want to use your calculator to find the roots. You're perfectly welcome to do that. But just say on the exam, found the roots with my calculator. Right? So just write that down. You won't get penalized, so you don't have to worry about it. But just let me know the steps that you're actually going through. Any questions about the exam? Yep.
What are the exam sections it covers?
I guess you could say it covers 2.8 through 5.5. I mean, it's going to cover all through chapter 5. But at the same time, chapter 1 was about the different systems, the row reduction. You're going to need all that knowledge. So you can almost say it's cumulative through the course.
Through 5.5?
Yep, through 5.5. So there definitely could be complex eigenvectors and values on there. Other questions? Yep.
Yes, but
Sure. Let me do one first. I did get one via email. So I want to go through this one real quick. So this is question 10 from 5.3. Anybody else have any questions about this one in the email I received? So the reason I asked is because I went through this one and I worked it out in preparation for today. And the student who asked that, I compared their answer, and I think their answer was totally correct. So I'm not sure why it was marked incorrect, so I changed the score on it. And then I also emailed Pearson to say, hey, what's going on? So I just want to make sure that other people weren't getting that same result. Because sometimes they can be quirky about formatting, so I don't know if it's just the fact that by convention we write our diagonal matrix from the biggest eigenvalue to the smallest, but that shouldn't matter. It should still be a valid diagonalization. So if Pearson's being too picky on their formatting, then you want to let them know that. So if anybody else, if you have a problem, you just can't seem to get it right, feel like you're doing it right, feel free to send me an email about it. But I think there's still a lot of good questions from this one, so we are going to go through it a little bit. So I want to diagonalize the following matrix. I'm going to first write out a battle strategy, if you will, here. The steps that I'm going to go through in this process. First step, I want to find my eigenvalues, find my lambdas. And to do that, I'm going to take A minus lambda I. I'm going to take that determinant. I'm going to find out what values of lambda make that determinant equal to 0. After that, I want to find my eigenvectors. And to do that, I'm going to plug in my eigenvalues into this. So I'm going to plug in the specific lambdas and solve this homogeneous system. After that, I'm going to let P as a matrix be a matrix whose columns are my eigenvectors. And then I'm going to let D as a matrix be a diagonal matrix that has the eigenvalues on the diagonals. And then if I've done everything correct, A should be equal to P times D times P inverse. Once I find P and D, that's the diagonalization of A. So, step 1, eigenvalues. Well, the eigenvalues are 7, 5, 4, and 4. Why did I do that instead of writing out the determinant of A minus lambda I?
Because it's a triangle matrix.
Absolutely. And that's something you're going to need to be able to recognize. So I could put a larger matrix like this. I mean, this is time consuming when we go through this. But I could put a big one like this and say, just find the eigenvalues. And if you have to go through that determinant process, it might take you a little bit longer. Right? So I don't like for time to be a factor, but you have to make sure we manage our time. We use the properties that are most efficient here. And so in this case, I can directly pull the eigenvalues. Now I'm going to plug them in. Now I can use any eigenvalue, but there's a specific one I want to use first. Which eigenvalue should I work with first?
4.
4. Why?
Because of its multiplicity.
Sure. So why does that make me want to use that one first?
Because you can cut down the number of steps.
Possibly. The idea is, at this point, I'm a little nervous. If I had 4 distinct eigenvalues, I could say there are for sure going to be enough eigenvectors to make a diagonalization. But now I have this repeated one. So I'm not really sure what's going on here. It is very possible at this point that I will not be able to have enough eigenvectors to actually diagonalize this thing. Right? I might get 1 eigenvector for 4, 1 for 5, 1 for 7. I have 3, that's not enough. I need 4 to form a 4 by 4 matrix P. So I'm going to do a 4 first, because if I don't get 2 eigenvectors from this, I'm done. And I can just stop and say it is no longer diagonalizable without having to worry about the other ones. So I'll start with this one. So when lambda equals 4, then I have my matrix A minus lambda I, which becomes, well, I'm just really subtracting 4 along the diagonals here. So I will get 3, negative 3, 0, 3, 0, 1, 1, negative 7, 0, 0, 0, 0, 0, 0, 0, 0. I'm going to use that to find my eigenvectors. So I'm going to give you a second here and see if you can work this one ahead and finish up finding just this eigenvector. Once again, the reason we stop and have you work these problems ahead of me is because a lot of these will make sense as I go through them. The question is, can you get all the way through the problem? You're going to be doing it by yourself on the exam. It's a good guide for your own studying. If you struggle with this problem, and you know that these are the problems you need to review. Of course, the other reason is why I didn't. Close, but what's x1? x1 isn't equal to this. We have to solve this for x1. And x1 equals. And then we gotta fix it. We solve this equation for x1. Well, this is not new stuff. This is just here's our matrix. So we'll tell you to solve the homogeneous system. This is A. So AX equals 0. How about find the solution? A blessing and the curse for this course is that we're just learning to do the same thing about 80 different ways and with 80 different names to it. So that's confusing, to have so many names and ways of looking at things. But at the same time, the nice thing is that the process is just the same thing we've done since the first couple of weeks of class. So at this point, we just have a homogeneous system. We have this matrix. I'll just call it B to make this look a little different. Bx equals 0 with our matrix. That's all we're doing is finding the solutions to that. That's just solving a homogeneous equation from chapter 1. So how am I going to solve this thing? I'm going to row reduce it. And I have to be a little bit careful here. When we talked about eigenvectors and the complex ones from 5.5, we said we have 2 rows here We know there's multiple solutions, so they have to be multiples of each other. But for a larger system like this, these rows certainly aren't multiples of each other. I know I had to get at least one row of 0, but I don't know if it's 1 or 2 or 3. For all I know, it could be any of those. So here I really have to write out the full solutions. So I'm going to row reduce. I'll divide that first row by 1 to simplify my numbers. Divide it by 3. So I will get this. Okay. Then I'm going to take and use this pivot position to eliminate the value above it. So I'm going to take row 1 and add row 2. And we'll get 1, 0, 1, and 1 plus -7 should be -6. So that's my RREF form. It gives me the equations x1 plus x3 minus 6x4 equals 0. The next line gives me x2 plus x3 minus 7x4 equals 0. Then I need an equation with x3 and x4. What's x3 equal to? x3, it's a free variable. What about x4? Also a free variable, just x4. So now as I write out my solution is just a set of values, x1, x2, x3, x4, that make this thing true. Well, x1 is equal to, well, I can just take my first equation here and solve it for x1. I have to subtract the x3 to the other side and add the 6x4 to the other side. x2 is going to be negative x3 plus 7x4. x3 is equal to x3. x4 is equal to x4. Now I have to write this in parametric form. So I'm going to think about this as x3 plus 0 times x4. That's the way I can think about it. And maybe 0x3 plus 1x4. And all I'm doing is writing it as x3 times all the coefficients to the x3s plus x4 times all the coefficients to the x4s. It's my parametric vector form for this solution. And I'm thrilled, very excited. I'm sure you are too. Why are we all excited here at this point, looking at the solution? Absolutely. I look at this thing, I'm finding the eigenspace associated with this eigenvalue. All the eigenvectors look like this. They look like a linear combination of these two vectors, these two eigenvectors. So the dimensions of this eigenspace are 2, which I'm very happy about. I'm going to have the vectors I need now. Didn't have to be that way. I might have had a dimension of 1 for this eigenspace, in which case I would be out of luck. But we're in luck, so we get to continue the problem. Woo. Okay. All right. Actually, I'm going to stop the problem there. I think we can kind of get through the rest. I wanted to work on this bigger system and go over a case where we had 2 eigenvectors associated with, as we plug in this one eigenvalue. But the rest, we just follow the same thing. We plug in lambda equals 5, lambda equals 7. We'll get eigenvectors, and then we'll form our big P times D times P inverse. So my plan is to stop here. I will work through it if somebody needs to see the rest, though. See the rest? Absolutely. All right, so we have these 2 eigenvectors associated with this eigenvalue. Now we'll try the next one. When lambda equals 5, we're going to plug that in. Essentially, we're subtracting 5 on the diagonals. So there's my matrix up there. So now I have A minus lambda I, which looks like 2, negative 3, 0, 3, 0, 0, 1, negative 7. And I got a negative 1 here and a negative 1 here. I'm just subtracting 5 on the diagonals. Now I'm just solving the system, right? This matrix times x equals 0. What are the solutions? So I'm going to do the row reduction. To do the row reduction, I'm going to leave this one the same. And I'm going to kind of talk through a couple steps here. All right, I have my next pivot position here. So my next goal is to eliminate this thing. So I'm going to add this row to this row. Gives me a 0 here. Gives me some number here. My next job would be to take this number and turn it into a 1. Well, I can definitely do that. I'll divide by whatever number it is, and it will turn into a 1. I don't really care what the number is. Okay? Once this is a 1, I'm going to use this 1 to do what to this?
0.
Turn it into a 0. So I'll have a 1 here, a 0 here. Then I'm going to use this 1 to do what?
So the one on top.
Eliminate this one. Eliminate this one. And I'm going to be able to do that because I'll just, if this is a 1, I'll just add 7 to here, and I'll add 3 to here. So I can do all that stuff. So because I can see how that process works, I actually don't need to do a whole lot of legwork here. I know this is going to end up to be 0, 1. I know I'm going to be able to eliminate that last row. I know I'm going to be able to come back up and eliminate these values as well. So that lets me do a row reduction pretty fast. And once again, the reason I can do that fast is because it's a homogeneous equation. So there is a right-hand side over here that's just all zeros. All right, once I get to that step, let's see. I guess if I want, I can also divide that first row by 2. I'll write out my equations. I have x1 minus 3 halves x2 equals 0. I have x3 equals 0 and x4 equals 0. I'm only missing x2. What is x2? Free variable, so it's just x2. My solutions look like x1, which is 3 halves x2. x2 is just x2. x3 is 0, x4 is 0. This thing looks like 3 halves 1, 0, 0. And I don't like that. So I'm going to change it. I'm going to say, what's my eigenvector? My eigenvector is 3, 2, 0, 0. Why did I do that? Because I could. Right? I have an eigenvector. Any multiple of that eigenvector is also an eigenvector. So if I multiply my eigenvector by 2, I get rid of the fractions, and it just looks cleaner. You don't have to do that. But remember, you're going to use this matrix to form P, and then you're going to have to find an inverse of it. And that inverse is going to be easier if you don't have a bunch of fractional values in there. All right, so that's that one. Then we go to lambda equals 7. All right. We have 0, negative 3, 0, 3. 0, see it was a 5 here, so when I subtract 7, I'll get a negative 2. 1, negative 7. This was a 4. When I subtract 7, I will get negative 3. And we'll get a negative 3 there as well. So that's me just subtracting 7 on the diagonals. I'm going to take this and do the row reduction. I will turn that into a 1, this into a negative 1 when I divide by negative 3. And then I'm going to take this row plus 2 of these rows. That will give me a 0 here. I'll have 1 plus 2 times 0 is 1. Negative 7 plus 2 times this thing, give me a negative 9. 0, 0, negative 3, 0, 0, 0, 0, negative 3. Same process as before. I'm going to be able to take this one and add it to here to get a 0. I'll have some weird number here. I'll divide through to turn this into a 1. That 1 will eliminate this value and both of these values. Once again, you can go through the full process. That's where I will get to. So, just kind of write it out in a couple steps here. This one will go away. I'll have some number here. I'll turn that into a 1. I'll use it to eliminate this thing. Then I'll use that 1 to eliminate this thing and this thing. I can write out my equations now. This tells me that x2 is equal to 0, x3 is equal to 0, x4 is equal to 0, x1 is my free variable. So my solution will look like x1, 0, 0, 0, or 1, 0, 0, 0. And the last step is just to take P And I'm going to write it like this. It's my eigenvector, and 3, 2, 0, 0. And I'll get my other two eigenvectors from up here. -1, -1, 1, 0, 6, 7, 0, 1. And then the eigenvalues have to match the order I did the eigenvectors, so this would be 7, 5, 4, and 4. And zeros everywhere else. And the last step would just be to calculate the inverse matrix. So A is equal to this, P inverse. All right. And it's part of my checking process because once again, a student emailed me about this and had this and entered it and it wasn't right. So I went through it in the calculation, like, boy, I got the same thing. Maybe we're both wrong, right? The easy way to check here is just to plug this into Mathematica, define P, find D, and then just take P times D times P inverse. Out popped A, we must have done it right. So it's a nice way to check our result as well. All right, any questions about this one? Okay, other questions? Yep. For a determinant or for an inverse or?
No, where it's, we have like a 3 by 3 matrix, for example, like a column. But
Cofactor.
So that would be the cofactor expansion to calculate a determinant. Okay, absolutely. So let's give ourselves a matrix A. 1, 2, 1, 0, 1. Okay, here's our matrix A. I want to find the determinant of A. Notice the straight lines on the side kind of indicate determinant. Now, the first thing I'm going to do is I'm going to expand this thing across the first row so we can really see the process. And then I'm going to do it two other ways, kind of via shortcuts, okay? So the first way is to say, all right, I'm going to expand along this first row. First, I'm going to assign all these values a sign. It's going to go positive, negative, positive. That sign comes from -1 raised to the sum of the positions. So the 1, 1 position, take the sum of 1 and 1, x to 2, -1 squared. This is the first row, second column, the 1, 2 position. 1 plus 2 is 3, -1 raised to third is negative. So they're just going to alternate signs as we go. So I'm going to take this value, I'm going to expand along this first row, that's +1, times a little determinant. The determinant I get when I eliminate the first column and first row. So the first row, first column. If I kind of imaginary cross those out in my mind here, give myself a big old highlighter. If I cross that out and I cross that out, I'm left with a little smaller matrix. My matrix is 1, 0, 2, 3. I'm going to find the determinant of that little matrix. Now I go to the next one. I have a minus sign, so that's -2 times another little sub-matrix. Now I am eliminating the first row, because that's the row I'm in, and the second column. I'm left with 0, 0, 1, 3. I go +1 times another little sub-determinant. This last one, what's my sub-determinant here? 0, 1, 1, 2. That make sense? Okay. Now in this case, I can calculate those subdeterminants. I basically have to do this until I get down to 2 by 2s because I have a formula for calculating those. So if this was a larger matrix, a 4 by 4, each one of these subdeterminants would be 3 by 3s. And I have to go smaller on each of them. So I'd have to recursively go down and down and down and down until I get to 2 by 2s. I'm at 2 by 2s here though. So this determinant is just 1 times 3 minus 2 times 0. This one is 0 minus 0, and this one is 0 minus 1. I get 3 minus 0 minus 1. 1, 2. Okay. Now, better way to do that. Expand along the second row. Right? Because as we can see here, I have these little coefficients to the determinants here. But if one of these coefficients is 0, well, that'll make it really easy. So if I expand along this row, I'll get 0 times the subdeterminant, plus or minus 1 times the subdeterminant, plus or minus 0 times the subdeterminant. So if I did it that way, I would have 0 times something. I figured out my signs first. This would be minus, positive, minus in this case. So I would get 0 times subdeterminant plus 1 times a subdeterminant, which is eliminate the same row and column. I'll get 1, 1, 1, 3, and then minus 0 times subdeterminant. And so I can do this one out, I will get 3 minus 1, which is also equal to 2. But it's easier because I chose the right row. Okay. Then there's yet another option. I could calculate the determinant by doing a row operation in A and making sure I understand how that row operation affects the value of the determinant. Because some row operations change the value of the determinant and some don't. But I do know that if I take this matrix and I take the third row and subtract the first row, that doesn't change the value of the determinant at all when I add or subtract rows. If I do that, I would get 0, 0, 2. Third row, subtract the first row. That doesn't change the value of my determinant at all. And I can see the value of this determinant. This determinant value is just 2. Because if I have a triangular matrix, the determinant is just the product of the diagonals. Okay? So 3 different ways to calculate that one. And a 4th little feature there. Any questions about that one? Yep.
For the triangular matrix, just get it down to R.
To do determinants, you have to be careful because when we're doing that row reduction, we can change the value of the determinant. So in other words, if I were to say, I wanted to put this in RREF, right, the next step would be divide this one by 2. That would take my determinant and divide it by 2 as well. But I have to be a little bit careful. So in general, when I'm doing a row reduction to find a determinant, I'm not going to bother putting in RREF. I might go to REF because I don't want to have to divide by values because that changes the value of my determinant. I also have to remember that if I switch rows, that will change the sign of my determinant. So if I'm just doing a determinant, I might do row operations just to get it to REF with these values here, and that would take the product of diagonals. But once I got to here, the determinant of this thing is just 1 times 1 times 2. Okay. All right. Any other questions? Any questions at all? Nothing. What's LeBron going to do in free agency? No, nothing. All right. All right, chapter 6 then. All right, a key idea for chapter 6. In real life, there often isn't a perfect solution to a problem. There isn't the one magical, unique solution. But instead, we must try to find the best approximate solution, the closest solution. That's oftentimes what we're really looking for. And so, what do we mean by closest? All right, that's kind of the big question here. For example, I want to find a line that passes through these points. And I have all those points plotted here in black. Well, those points are not linear. They don't all lie on the same line. But that doesn't mean I don't want to find a line that's close to passing through them all. Right? I want to find a line that's closest to hitting all these points. So that's often what we're looking for. So I can't take this thing and put it in some matrix and find a solution. But I still want to find a way to find this line. I want to find a way to approximate the solution, to find the best or the closest line to this solution. All right, so there are two concepts here that we're really going to need. I mean, so how would we even think about this problem? Like, how would you tackle this problem? Like, is this line closer or is this line closer? Which is the better fitting line? Red or black?
Black.
Black. Why?
Closest close.
Maybe it's closer.
The points are
Oh,
closer to the black line.
The points are collectively closer. How did you figure that out? How did you measure the distance from the point to the line?
visual.
Because of where
Let's see. Let me draw this one. There, and looks like it's closer to the red line. Obnoxious, right? All right, well, we measure this distance. We're going to measure something that's perpendicular there. That makes sense. I mean, I could draw any kind of line like this. That doesn't really give us the length or the distance from the point to the other vector or the other line. So to measure how close things are, I need some sense of perpendicular, right? Because the quickest way, the shortest distance from this point to this line is the perpendicular. So if I measure how far is this point away, that's what we're measuring, whether we're thinking about it or not. We're talking about the perpendicular distance to it. So I need a sense of what does it mean to be perpendicular in general to talk about closeness. So I need two concepts. I need a concept of distance and perpendicular. Perpendicular, or as we're going to call it, orthogonal. Orthogonal. I need to apply this to vectors in general. Right? So I need to say, how long is this vector? What's the distance between this vector and this vector? I need to find out whether those two vectors are perpendicular or not. So how are we going to do that? We're going to do that with a thing called the dot product. We're talking about the dot product. If you had Calc 2, we talked about the dot product in Calculus 2, so this will be a review of some of those things. Many people haven't seen the dot product before, so we are going to go through it kind of from a base 1 level here. We're also going to generalize the dot product to mean something bigger, not just for the vectors in R2 or R3, but in a general vector space. So we want to learn how to calculate it, its key properties, and to generalize it to an inner product, which is what it really is. We'll start off with the calculations. Now the nice thing about defining this dot product is we actually have two different ways we can define it, algebraically and geometrically. So we'll do both and talk about both those properties. Here is its definition for the dot product. The dot product of two vectors u and v. It's got an algebraic definition and a geometric definition. All right, algebraically, u, the vector u dot the vector v is the product of the components all added together. So u, the first components, that product, plus the product of the second components, plus dot 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 to the product of the last components. Right? So if I have the vector 1, 2, 3 dotted with the vector 2, 4, 6, I take 1 times 2 plus 2 times 4 plus 3 times 6. And I get some number answer. So the dot product is going to be a real number. In fact, it's also known as the scalar product. This is the fancy notation for that, using the summation notation. Now the geometric definition says u dot v is the magnitude of u times the magnitude of v times the cosine of theta. So the first question we should ask is, what is this magnitude thing? Right, the magnitude is the length of the vector. This is the magnitude of v. It's the length of the vector v. And if we're in one of the R spaces, R2, R3, R4, we calculate that as the square root of the sum of each of its components squared. So v1 squared plus v2 squared plus v3 squared plus dot 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 plus vn squared. Right? And you've probably seen that before. Oops. So this vector v is the vector 3, 1, and I want to find its length. I kind of use pi tag here. I say this squared plus this squared should be this squared. So I take 3 squared, add up to 1 squared. That's the sum of the squares, 3 squared plus 1 squared. Should give me this thing squared. So this length is the square root of 3 squared plus 1 squared. So that's v. The magnitude of v is the square root of 3 squared plus 1 squared. All right, so the geometric definition is the product of the lengths times the cosine of the angle in between them. So there's my theta that I've drawn in there, cosine of theta. That's the algebraic definition. Now there's certain properties that are applied to these definitions. Algebraic set of properties and a geometric set of properties. So algebraically we have these 4 properties that we could really go through for the dot product and verify that all these things are true. We have names for some of them. What's the name of the first one? Commutativity, absolutely. Commutativity. And at this point now, we can realize that that's not a trivial thing because that doesn't always hold, right? We talked about matrix multiplication where commutativity did not hold. So it's important that we say, okay, we have something new. We're defining a dot product. Is it commutative? Is it associative? Do all these properties hold? We find out it is commutative. Now what about the next 2? The next 2 I can kind of pair together, actually. I can say the first one is kind of a distributive property. And the second one is an associative property of scalar multiplication. But they're actually kind of more than that. They tell me something else about this operation of the dot product. Dot product is acting on certain vectors here. And so if it acts on the sum of the vectors, the result is the sum of the dot products. So if I had an operation that was acting on a u and a v and mapping it to whatever that dot product value was, what I'm doing is I am applying it to a sum of vectors, and I'm seeing that this number is related to that. It's just dot product here, sum of dot product here. Same thing with a scalar. So I'm taking the transformation on a scalar. The scalar is just kind of built in there. So really, both these combined are giving me a form of linearity. And then the last one we're going to call positivity. It says that u dot u is greater than or equal to 0, and u dot u is equal to 0 if and only if u is equal to the 0 vector. All right, we can't take the dot product times of vector times itself and get a negative value. And if we get 0, that means the vector was 0. So we have kind of some stated properties. Then we might think of geometric properties, and here we're kind of going to deduce these properties. We're going to think about what happens in some special cases. So for instance, if I take u dot u, I can actually use this geometric definition. Well, if it's u dot u, I would apply my formula here, magnitude of u times the cosine of theta. But what is theta in this case? Zero, right? Theta is 0, so what's the cosine of 0? 1. So it turns out to be just this. So the dot product of u dot u gives us the magnitude of u squared. If we just flip that around, that tells us that the magnitude of u can be represented in terms of the dot product. It's the square root of u dot u. And this is an important feature, one of the most important features about the dot product. And we have these two different definitions. We have an algebraic one, we have a geometric one. And they're related together. So now, as I generalize the dot product of vector spaces that I don't know what they are, they're not R2, R3, they're collections of fruit. If I can define an inner product, a dot product, I can talk about the length of that thing, just in terms of however I define the inner product. So we're going to talk more about that later. That's the first geometric property. The other one would be, what happens if u is perpendicular to v? If u is perpendicular to v, and I take u dot v, what's theta then?
90 degrees.
90 degrees. And what's the cosine of 90 degrees? 0. All right, so in this case, that dot product equals 0. So now we have a test to see if these things are perpendicular or not. So this one calculation, the dot product, or we're going to generalize the inner product, gives us both the properties we need to talk about distance and geometry and vector length. It tells us how to tell if vectors are perpendicular. We just check their dot product to see if it's equal to 0. It also gives us a way to measure vectors just by doing this dot product calculation. All right, so that's where I'm going to stop today. The last thing I'll say is, so the exam is tomorrow, so prep for the exam. We're really going to start 6.1 fresh again on Monday, but we're going to have to not be able to fall behind, and there's a lot of definitions in section 6.1. So we are going to have a reading quiz on 6.1 at the beginning of class over the basics of the section, not the most complicated stuff, but just the basics. So make sure you prep for that for Monday.
Could you roll it back to the property?
Sure. All right, so that's all I have today. Prep for the exam for tomorrow. This one?
Yeah.
Okay.